I'm Mark Stewart, a Director of RSK Geosciences, and welcome to our November edition of our 2025 series of Down to Earth webinars. These will cover a broad range of subjects and are always available on our YouTube channel alongside previous talks. So our talk today is going to be given by Craig Towell, a Principal Engineer within our Utility Surveying team. Craig is going to talk to us about the use of geophysics to map highway structures. So firstly, I'm just going to run through a quick bit about housekeeping during the talk. So all attendees' microphones are automatically muted throughout the webinar. During the presentation, you can post questions online, and there will be a Q&A session at the end of the presentation. We will answer as many questions as possible at the end of the talk. Those that can't be answered due to time constraints will be answered after the webinar by email. Shortly after the webinar, you'll receive a link to a short survey. If you could take a few minutes to provide feedback, please, so that we can improve on future webinars, that would be fantastic. So now let me introduce our speaker today. Craig has over 17 years experience in geophysics and surveying and is based in our RSK Geosciences SafeGround team in the Southwest. Craig's a chartered scientist with the Geological Society and has extensive practical experience of surveying structures and utilities in a broad range of environments, including highways, rail and structures. So now I'll hand over to Craig to provide an introduction to the challenges of surveying beneath the surface of highway structures. So Craig, over to you.
Thanks, Mark. Welcome to this week's DTE webinar, which will be covering the use of geophysical investigation methods for the assessment of highways and highway structures. In particular, we will focus on ground penetrating radar, GPR, which is by far the most commonly used geophysical technique within this context. We are going to look at what GPR is and how it works. We will look at the relevant standards and legislative restrictions around its use. We will look at how the surveys are conducted and what kind of deliverables can be outputted. Finally, we will look at some data examples from the various survey types and objectives. We will begin with a look at what GPR is, how it works, and why we use it. The image there is just one of our vehicles with a bit of trim missing, unfortunately, with one of our towed GPR array systems. So GPR is the most commonly used geophysical technique for highways assessment, as huge amounts of data can be collected rapidly with minimal disruption to traffic flows. As the technique is non-destructive and mostly non-contact, that means the data can be collected safely and quickly from a moving vehicle. We can cover up to several kilometers of highway within a single shift without the need for any TM, and it can be economically deployed to carry out surveys across even entire local authority road networks. Or it can be deployed to target specific small areas where issues may be occurring within the road. GPR itself, it's what's called a ping and listen technique, in that it sends out a pulse of electricity, a pulse of energy, and listens for the echoes of that pulse when they bounce off something. It's a bit like sonar, but with radio waves rather than sound waves. These radio waves travel at the speed of light in whatever medium they're traveling through, and so the GPR electronics requires accuracy down to fractions of a nanosecond, which does make for some expensive equipment. A high-end GPR system can actually cost as much as a house, although base model sort of single channel systems can be had for about £30,000. By using GPR, we can detect and map changes within the pavement construction, and can also detect troublesome areas such as saturated layers or voids. It can also be used for post-construction verification to check that the pavement layers have been laid to the correct specified thickness. GPR is a specialist technique, and to get the best out of it requires real investment. On top of the purchase price of the equipment, the use of GPR requires significant training time for the operatives and for those processing and interpreting the data. A minimum of around 6 months of training for our staff within Geosciences has to happen before they are let loose with a GPR system on their own, although most will have already used GPR in some aspect as part of their geophysics degree. We do like to have the same people processing and interpreting the data as that collected it, as we find that that generally yields the best quality results. As previously mentioned, we can tailor the depth of the investigation by choosing different frequency of antenna. However, the trade-off is that the deeper you want to look, the worse your resolution is, as seen in this chart of vertical resolution versus frequency. A 50 megahertz antenna can penetrate down to several meters into the ground, but it is not going to detect any layers thinner than around 250 millimeters, which is not very useful for pavement assessment. We typically use a multi-channel GPR system coupled to 3 or 4 antenna with frequencies of between 400 megahertz and 2000 megahertz, which allows us to detect fine structure within the pavement while simultaneously seeing down into the subgrade and natural formations beneath the road, all in a single pass of the vehicle. So looking at the sort of relevant standards and legislative restrictions, there are several that cover the use of GPR. So GPR surveys on public roads in the UK must operate within specific legal and technical frameworks. So we've got the radio licensing. So although we try to always direct the radio energy into the ground, and the transmit power is very low, probably a fraction of a mobile phone transmit power, the GPR system is technically broadcasting radio waves. And so all GPR operators must comply with Ofcom regulations on radio frequency broadcast and operate with an Ofcom GPR license. As part of that license, if we wish to work near sensitive sites such as airports or radio astronomy sites, both of which can suffer interference from our transmissions, we need to follow specific procedures to notify those sites. European standards, there are the ETSI EG 202730 to ensure they are safe and interoperable and legally compliant. The ETSI standard sets out approved frequency ranges and power limits for the equipment. It sets out operational safety to prevent interference with other systems, and it also outlines best practice for survey methodology and data handling within Europe. Here in the UK, we have the Design Manual for Roads and Bridges, the DMRB, and CS229 covers pavement assessment in various ways, but it also has a section on GPR surveys. Indeed, we are commonly asked by clients to carry out a GPR survey in accordance with CS229. However, CS229 is not in itself a specification for a GPR survey, and generally much more detail is required from the client in the survey request. Other standards may be applicable, such as PAS 128, which is the publicly available standard from the BSI for detection and mapping of buried utilities. It may, a client may wish to perform a utility survey alongside the GPR pavement assessment, and so that's a situation where that would come into play. So now we will look at what we need to think about when we are planning a GPR survey, including what information we need from the client and considerations on how we are to safely conclude the survey whilst meeting the objectives. So planning. Right at the start, we need information from the client on what they want the GPR survey to achieve. So that would include the objective. Do they want information on layer thicknesses, anomalous zones such as moisture avoiding, buried utilities, or all of the above? How much of the road needs surveying? Could just be a single bridge deck or several kilometers between junctions. Survey coverage. Do they want a single profile in the near side wheel path, or full width of each lane covered, or somewhere in between? Do they want transverse profiles as well, or not? How is the survey to be georeferenced? Is it to be positionally referenced to a scheme chainage? It can be referenced to OSGV National Grid, or it can be simply referenced to the marker posts alongside the road in the case of major roads and motorways. Will any necessary traffic management be supplied, or do we need to organise it ourselves? Generally, TM isn't required, but certain objectives, such as the transverse cross sections, if they are required, may actually need TM. The more information we can get at tender stage, the better we can design the survey, and the lower the survey costs will be. If the objectives are vague and unspecific, we end up throwing everything at the job just in case, we don't know what the client wants, so we'll try and get everything kind of case. And generally that ends up costing a lot more. Once we know what we are going to do on site, we can prepare the survey plans and risk assessment and method statements, which can be shared with the client for review and comment. And after that, we can start preparing for the actual going to site and the layout of the job and how we're going to do it. So GPR data, it does need to be calibrated in two ways, essentially, and you can think of it as vertically and horizontally. So vertical calibration is required to get accurate depth information. What the GPR measures, the raw data it measures, is the travel time, the two-way travel time. So that is the time it takes for the radio wave to travel out into the ground, to bounce off something, and then to travel back to the antenna to be recorded as a trace. So essentially what we got there is just simply time. So in order to get the distance, which is what we need to know the velocity of the wave. So essentially, how do we get the velocity, which is going to give us the distance to the reflector? So the least accurate way to get your velocity is to simply use a textbook value. Various publications will have charts of velocities for various kind of materials that you could find within a pavement construction, and the easiest way to do that is just to apply one of those. Look at the construction of the pavement that you've just surveyed and apply one of those textbook values, and it will get you roughly in the right ballpark. But it's not the way we like to work. We can use a much more accurate way, which is by using existing core information to compare the known thickness of the layers as measured in the core logs and comparing it to the measured thickness in the GPR data. And that way you can calibrate the velocity to get accurate depths. So ideally, we need to know the existing core locations before going out to do the survey, so that we can make sure that we pass directly over them with the GPR system for the best results. Or sometimes cores haven't been taken yet, so we'll be asked to look at the GPR data and identify any areas that we would like to be cored, and so we can pick them out, and then we would give the exact locations in eastings and northings to the client. They would then hand them over to the coring company and then go out and take the cores from the exact spots. So either way works all right. I generally find that existing core information would be best, because we can make sure that we pass right over it, and that's essential really for best results. So horizontal calibration, this is usually known as a survey wheel calibration. It's just making sure that the system thinks it is traveling along the road at the speed it is actually traveling along the road, and it's transmitting its pulses at the correct rate. Usually that's simply done by just laying out a tape measure at the side of the road, generally around 10% of the distance you're going to collect. So for example, if you know your GPR profile is going to be 1 kilometer long, you'd probably want to calibrate your survey wheel over at least 100 meters for best accuracy. And then you simply just drive that 100 meters along the tape measure, tell it when to start, tell it when to stop, and then it will have a value of how many ticks the odometer wheel will output, and that can be used to make sure that it's transmitting at the correct rate. So yeah, essentially doing that, you're making sure that the position laterally along the road of your data is accurate and well known. So looking at reporting requirements, essentially at tender stage, we would ask the client what kind of deliverables they require. And a client may not know what can be done, so we would inform them, exactly what we can do. In CS 229, it does give some examples of deliverables, and so clients will often ask for, the deliverables that are outlined in CS 229. But generally, the report or the deliverables would include a written survey report outlining everything about the survey, how we planned it, what we did, what the weather was like, what the limitations were, etc. It will almost always include something called construction charts, which are 2D graphical drawings showing a cross section along the road and showing all the thicknesses and anomalies of, within the layers. It could include tabular outputs of chainage and thickness for each layer in a CSV format. And clients will want that to upload to a pavement management database. It can include 3D data interpretations such as depth slices and amplitude plots, which can help to make the information that the data contains much more easy to interpret and much more easy to visualize from the client's perspective. So really any combination of those or all of the above is something that we would normally produce from a pavement assessment survey. Excuse me. So what exactly are we looking for in the data? This depends on the scope and what the objectives are, but generally we're looking for sub-horizontal or horizontal continuous boundaries within the GPR profile. Those represent the layers of the pavement construction, and sometimes we can see, you know, layers that go all the way through the data. Sometimes layers come and go, and sometimes layers are just invisible, essentially. So that's what we're looking for as a kind of number one. Additionally, we're looking for indications of structural steel or rebar, which you'll get in concrete roads and especially on bridge decks. We're looking for other things, other features in the data which could indicate construction changes, so rapid changes in thickness or changes in material, where the construction completely changes from sort of one meter to the next. We can be looking for unknown utilities or culverts beneath the road or within the road. And we're also looking for anomalous areas within the data, kind of bright spots or dim spots or something that can indicate voiding or delamination between pavement construction layers, or even moisture contamination within the road. And basically anything that we think the client might want to know about is something that we can pick in the data and put on the construction charts to give to the client as a deliverable. And also, you know, as part of those construction charts, they're going to be cross-referenced within the report, where we'll give data examples of what we've seen and talk about generally what we think this anomaly might be. So looking at the construction charts themselves, they're easy to visualize method of presenting the results and usually looks something like this. The scale has been cut off in this screen graph, but the vertical axis is depth and the horizontal axis is distance along the road. We generally aim for consistency between projects on how these charts look, but the client may specify the format that they want them to be delivered in. The charts could have a plain white background just for ease of visibility like this, or they can be overlaid on a semi-transparent image of the data itself. So you can actually give an indication of what the data look like as well as your interpretation at the same time. They've generally got other features on there, such as the vertical red lines, which indicate a construction change. We can highlight manholes and inspection chambers. We can highlight the rebar, base of concrete, base of bound material, subgrade layers, internal asphalt layers, and yeah, areas of voiding and sort of moist, what we think might be moisture contaminated, can be highlighted on these charts as well. So as well as the construction charts, we can give other 2D and 3D visualizations of the data to make it easier for the sort of layman to understand what is going on. Here we've got some data examples of, well, actually the GPR data on the left is an example of a transverse profile across the road instead of along the road. Normally in pavement assessments, you're running along the road in the direction of travel, but sometimes we need to collect data across the road as well. So what you can see here is some very localized increases in depth. So essentially that is severe rutting within the asphalt construction's pavement. This particular example, the road was not designed for HGV uses, but due to changes to the local network, it ended up carrying a lot of HGV traffic, and it just wasn't up to the task. So it rapidly deteriorated, and you had a lot of very deep, very severe rutting, as you can see there. The purple chart is a plot of the depth of the base of the bound material, which is the base of the asphalt, essentially. So you can see it quite severely deepened, and then essentially it was just tarmacked over again and again and again, so resulted in localized deepening of the asphalt. This particular one, we have examples of depth slices or time slices, what we call. So we take very dense data collection, so lots and lots of data profiles rather than just a single profile along the wheel path. And we can combine them together in software to form essentially a 3D cube of data. Interpolation occurs between the lines. And you can then slice through that cube and take the values. So these charts are showing amplitude at various depths, 0.1, 0.2, 0.3, and 0.4 from the surface. And what they are, again, there's no scale on this, but these are plan views. These aren't 2D cross sections. These are bird's eye view of the road. So we're looking down on the road. So the sort of x-axis is along the road, and the y-axis is across the road. And the colors represent the amplitude of the reflected signal. And generally, not always, but generally, higher amplitude reflections can indicate voiding or moisture or some other issue. And so in these charts, the red colors is where we've got the highest amplitude, and the blue colors is kind of low background amplitude. So yeah, we can target these. In this instance, it's just regular intervals through the road construction, or they can be targeted at a specific layer. So the client may be interested in any voiding at the base of the bound material, which could be the base of the asphalt or the concrete. And so we would pick out that particular boundary and tell the software we want to plot the amplitude all along this boundary, and it'll give you a chart like this. So we can say to the client that here is where you've got specific areas of trouble at the base of the bound material. So the importance of prior knowledge. Here we have an example of the importance, or how important it is to be given information before we go out. Well, maybe not before we go out, but certainly before we start interpreting the data. On the left is an interpretation of some GPR data. Again, this is a top-down view, so we can see essentially what is a kind of a bridge deck here. On the left is the interpretation of the data with no prior information of the road construction given to us. Essentially, every high amplitude anomaly was treated as a potential void or defect, as we had no real reason to say they weren't a void or defect, and so they were identified as that on the plan. The client was obviously somewhat concerned with the results, and so they actually were quite motivated to go out and seek some as-built information, and they found some and gave it to us. So we then went back to the data and reinterpreted it with the as-built information in hand, and so we could see essentially the structural elements of the bridge, and what was previously classified as defects were actually parts of the structure of the bridge, and so we were able to reclassify those anomalies, which made the situation look much better, essentially. And the anomalies that did remain were essentially low risk, and yeah, they were classified as low risk by the pavement engineers who were looking at the data. So examples of other applications. So far we've looked at the main application for pavement assessment, which is just layer thicknesses and changes in construction. However, there are several other applications for GPR in the highways environment we can look at. So layer thicknesses, so the main one, buried utilities, another key highlight for GPR, moisture detection, which I could talk about in a minute, crack, void, delamination detection, material type identification. So yes, generally possible to identify material types in good quality data, and mapping of structural features, e.g. on bridge decks or you know, structural steel and rebar and things like that. So focusing on moisture mapping, here we have some examples of a project that we did back in 2016. So we carried out a GPR survey on the lifting bascules of Tower Bridge in London, and they have a plywood construction element with a thin overlay of asphalt. They had to be lightweight in order to be lifted, so that's why it's been made out of plywood. The client had concerns about the longevity of the plywood material and was specifically worried about moisture getting in and deteriorating the wood. We carried out some experimentation in the office, in our workshops after the inquiry, and we were able to develop a technique and a methodology to detect and measure the moisture within the plywood, which essentially involved measuring the apparent thickness of the wood as it appeared in the GPR data. We found that from existing core material, we found, for existing core samples, we knew that the plywood thickness across the deck was very well controlled, and it had a very even layer of wood across the whole bascule. So we knew then that any apparent thicknesses in the GPR data must have been due to the moisture within that wood, because the moisture affected the electrical properties of the wood and caused the GPR wave to travel more slowly, which increased the two-way travel time and essentially made the wood look a lot thicker. So the examples here show the processed GPR data, sort of lower left there. You can see the various layers within the bridge deck, and then the underside of the deck, which was kind of sort of vaulted arch shape. We see the 2D plan of the moisture map at the top there, the blue and red. Again, the red is areas where we think there is moisture contamination, and the blue is the sort of drier areas. This also on there is the cores that were taken, and some of them were targeted as well by us. And then we have a chart there showing some moisture content as measured from GPR versus the actual oven dried moisture content taken from the cores, showing quite a good correlation. We wouldn't normally try to offer actual values of moisture content from a GPR analysis, but we were, because we knew what the specific elements about the wood itself, and we were able to apply some equations to come up with some. It was a very experimental kind of feature, but we were able to provide some estimated moisture content values, and they were generally in fairly good agreement with the actual values. So the client was very happy with that. They unfortunately used these results to justify closing the bridge to all traffic for about 3 months in 2016, which was obviously a huge disruption to local traffic. I lived in the area at that time, so it was essentially my work that helped to close the bridge and disrupt myself. But it was a great project, and the client came away very happy. So we were very pleased with that one. Aviation, so as well as obviously roads and highways, we can perform pavement analysis surveys on runways, taxiways, aprons, airports. The fundamental principles are the same. However, the pavement construction can be different. There can be much thicker layers of concrete and asphalt, which can mean we need lower frequencies to see all the way through them. There's also obviously some specific health and safety considerations to work in this environment. You may be on and off quite quickly in between flights, or just doing everything at night. And obviously there's a consideration as to the frequencies you're using with, and whether they'll interrupt with the air traffic control radar frequencies. Another application could be crack detection. So generally we can collect high density data over existing cracks to assess how severe they are and how deep they go into the pavement construction. Because these aren't, these are very small areas that we're surveying essentially, and we do them on foot. So these would normally require traffic management. but they can be quite useful for characterizing cracks, and then giving that information to pavement engineers to be able to prioritize what they need to fix first. And then the last kind of one we're going to look at is the buried utilities survey. So these can often be instructed alongside a pavement assessment survey. As you're using GPR, you're kind of using it in different ways, but you can do them together, especially with the use of sort of modern high density towed arrays. Essentially, yeah, we can produce a map of the utilities. Generally, it's a lot more involved and more time on site, because we have to actually, it's not just GPR. We'd have to do cover lifting and EML tracing and things like that. But it's something we can do if needed. So yeah, conclusions. Just let's have a look at the last slide now. And so conclusions: ground penetrating radar provides a safe, non-destructive way to see beneath the surface. We can map pavement layers, moisture and defects without excavation and in a safe and economical manner. By following guidance like CS229 and related standards, the GPR can deliver reliable and defensible data that supports maintenance planning and asset management decisions. By aligning with UK and European standards, the surveys can ensure data accuracy, legal compliance and interoperability across the UK's road and runway networks. And that is the end of the presentation. Thank you.
Thank you, Craig. Yeah, very interesting talk, touching on a lot of the different aspects of the work you're doing and the different types of sites. I know you're doing other sites with us, like water treatment works, etc. So very busy time. I've got a few questions here we can go through. First of all, how wet does the road surface need to be before you would not consider doing a GPR survey?
Yeah, quite wet. Actually, in CS229, the DMRB section, it does actually give a warning not to do GPR surveys if the road has been recently salted, or if there's excessive water on the road. The reason for that is because the salt increases the conductivity of the pavement materials, which basically has a negative effect on the GPR data. And when it comes to wetness, you know with a damp or just generally wet surface, it's usually fine, because we use almost exclusively ground coupled antennas. So we've got antennas that are actually in contact with the ground instead of being launched from the air. And they're not that affected. But if there is standing water and puddles, then we would avoid it then, because that layer of water can really hamper the GPR, and it can also damage the equipment as well. And we've already kind of said how expensive it is. We don't want to be damaging it with water ingress. Okay,
good. So at what point would you need traffic management to carry out one of these surveys?
Yes, good question. I think so normally, well, it depends on what the client wants, essentially, because we can travel along the road with the van and the equipment towed behind, and we can generally collect the data at traffic speed. So if the client wants longitudinal profiles, that's fine. We don't have to choose. On very high-speed roads, motorways and stuff, we may have a blocking or a buffer vehicle behind us with extra sort of signs and flashing lights, but whereas we will be traveling a little bit slower than sort of 70, but we can get away with that traffic management for any kind of work like that. If the client wanted sort of utilities information, we would need traffic management there to do the cover lifting and stuff. If they wanted transverse cross sections across the road as well as along the road, we would need to either collect a high enough density of long profiles to build up a cross section, or if they actually specified they want GPR data collected transversely, we would have to have traffic management, because we'd be effectively walking across the road. We can't drive the van across. It's not wide enough. So we collect on foot across the road. So we would need traffic management then. But pretty much all other times you can do it without. Really saves money.
And can we sort that traffic management out?
Yeah. So within RSK there is traffic management companies, so we can get that quickly and cheaply. So it's something we do all the time.
Excellent. One more question. So there's still some time if anyone wants to drop a quick question to us. It's around post-processing. How long does it take? Maybe just comment on how important it is.
Yeah, so the post-processing is essential. So you have to, when you're collecting the data, there's various sources of noise which can sort of degrade the quality of the data. So it's hard to interpret on site. In the office, you can run it through software to reduce that noise and increase the signal to noise ratio to make it more easy to interpret. Makes it easier to see sort of deeper layers and to pick continuously along the road. So yeah, it is essential. And again, it depends on what the client wants that will dictate the reporting times. There's sort of two kind of phases. So you've got your data processing and interpretation, where you're actually looking at the data, you're picking features out in it, and then after that you're producing your report. So you're making all those wonderful looking charts and tables and whatnot. So that can take some time as well. So, but generally, a day on site might produce sort of 3 or 4 days of office work reporting time. And a large scale project will obviously produce a lot more, but we can generally run it concurrently with the site work. So the site work will start on week 1 and then reporting will start on week 2, and so we'll still have those end deliverables with the client a couple of weeks after finishing on site.
Okay, fantastic. Okay, well, we'll draw to a close there. Thank you, Craig.
No worries, thank you,
our
Mark.
next Down to Earth talk will be on Tuesday, the 9th of December, and we'll be looking at the benefit of engaging geoenvironmental assessments early in the planning process. So please remember to complete the feedback form and join us next time. Thank you very much.
Thank you.